Thanks for coming. I was afraid being in the biggest room that it was going to be me and our host and the website guys, and that's about it. If you're not familiar with WhatsApp, we have a multi-platform smartphone messaging app. And we're at this conference because most of our server systems, our backend that does all the message routing, is done in Erlang. And so a little bit about me to start. I joined last year. I'm new to Erlang, so if at some point during this talk the thought pops into your mind, well, that's obvious, or why'd you do that? There's this, and bear with me a little bit. We're still learning some of the intricacies of using Erlang effectively. But I think we've made good progress, and we want to share some of the things that we've discovered and some of the results, because we feel like it's been a pretty solid and performant platform, and it just continues to kind of amaze me. My background is in mostly C. I was previously at Yahoo. I spent 12 years there, working on a lot of scalability and data caching types of problems there, network routing, things of that nature. So let's get into what we're going to talk about today. So first of all, I'd like to start with just kind of a problem statement. Some of the performance goals that we set for ourselves, and we've been trying to push the envelope there. Some of the tools and techniques that were instrumental in helping us improve the scalability of our systems, some of the results to date, and then some general findings about scalability of Erlang in our environment, and then I'm going to go through some of the specific scalability fixes that we've implemented in the code that we're running. So the problem. Unfortunately, my labels are the wrong color here. So there's sort of three fundamental problems here. We've got our user growth. So if you look at this graph on the left, that's our messaging traffic over the past 4 weeks. So you can see it continues to climb, which is a good thing. We're very excited about that. But of course, that makes the people who write the checks nervous, because that's going to eventually mean buying more hardware, which drives up our costs. And it also creates more operational complexity the more systems that we have to operate and keep running. So there's just sort of the organic growth that we're going through, but then we also have to build into the system enough resiliency to deal with unexpected things. So I just happened to be grabbing this graph the other day when I was putting these slides together, and I noticed this little bump there on the left-hand side, and I thought, oh, that's kind of strange. So I went through our country-by-country graphs, and there was a big bump in Mexico. And so when we see bumps like this, we go to the news. We just go to Google and we search for news for Mexico, and of course, that was an earthquake. Often these little bumps that we see are one of two things. They're either earthquakes or they're soccer games. So the one on the right is a soccer game in Spain. So you can see we have halftime. Here's this first bump, then here's a goal, and there's full time right there. So it's kind of interesting, but of course it creates a challenge, especially when these things happen close to our peaks. We have to make sure that we have enough extra capacity to deal with those types of incidents. So the problem, our initial server loading was about 200 simultaneous connections per server, which, when we extrapolated out where we hoped we were going, was going to be a pretty discouraging prognosis for growth in terms of how much money and operations time we were going to be spending on server hosts. And further, the cluster was a little brittle in the face of those kinds of overloads where we got close to or exceeded certain limits, or we had we'd have little networking glitches or things like that. We needed to we needed to figure out how to decouple these things a little bit so that things weren't so brittle when we were running them at a pretty high capacity. I mean, obviously we could run with 75% overcapacity, and we'd probably not run into these issues. But that wasn't the kind of efficiency we were looking for. So that was the initial problem. So sort of the initial goal was, and I kind of was in a little bit of disbelief when I was first presented with this goal of 1 million connections per server, because despite having worked at Yahoo on scalability, one of the probably top 5, certainly top 10 traffic sites on the internet, we didn't talk in terms of millions of connections per server. We had many, many servers to deal with the traffic there. Now, there's a little bit of a difference because we kind of have a very homogeneous traffic load at WhatsApp, whereas Yahoo has many different types of properties that they're serving, and so the characteristics are a little bit different. But still, 1 million seemed pretty ambitious, especially when we were running at about 200K at that point. But then, obviously, in conjunction with that, if we're running our servers with a certain amount of headroom to allow for world events or hardware failures or other types of glitches, we're going to need enough resilience when we're running at those fairly high usage levels to deal with these other things that are going to go on. So, so this is the standard configuration we use for our servers that we do our connections with. These are basically the user-facing server hosts. They're dual Westmere hex cores, so that's 12 real CPUs with hyperthreads, meaning 24 logical CPUs. We load them up with RAM, and we run them with SSDs. They have dual NICs, so the user traffic comes in on a public interface, and then all the back end, all the distribution runs on a private network that's on the back on a separate NIC. We're running FreeBSD 8.3, and currently we're running on R14 B03. So now I'm going to just talk a bit about some of the tools and techniques that I've been using to increase our scalability. And I'm sure you can't read that at all. The first tool, basically the first thing I did when I got to WhatsApp was I wrote this tool, which was pretty similar to a tool I wrote at Yahoo. It's a system activity recorder. So basically it allows us to record system stats across the system, including the OS stats, the hardware stats, beam stats. It's modular, so if we want to add a certain, we want to monitor metrics from a certain, from beam or from virtual memory system or from the network, we write a module for that, and so it's easy to plug in new stats. So I'm going to zoom this in a little bit. There we go. Thought I was. Yeah. Let's go back. There we go. Not the best resolution, but basically, up here are some of the OS level stats that we track. CPU utilization, so it's got overall utilization, user time, system time, interrupt time. And there's different levels that these can be displayed. So it's actually, for CPU, it's also tracking things like context switches, system calls, traps. But this is a reduced set of things that it's displaying right now. For TCP, we've got packets sent, packets received, retransmit rates, listen queue overflows, connections per second, PCB counts. We also track things like sync cache overflows, all those types of things. We've got virtual memory over there, so overall utilization, active, inactive, cached, and so wired. And then down below, I've got the beam stats. So my first Erlang code was the module that exports these beam stats so that WSAR can extract them. So we look at things like what's the total count of messages and all the queues across the processes. Are there any, have there been any busy port events for either the disk ports or the normal ports? What's the disk message traffic rate? Bytes going in and out. We've also, operator error here. I've also got some scheduling stats here. Percent utilization in the schedulers, context switches, waits per second, sleeps per second, reductions, kilo reductions per second, how many garbage collections are happening, how many words are getting collected, and so on. So originally, this tool was run once a minute, and basically would take a snapshot. But as we got further and further trying to drive these systems harder, it became clear that we really needed 1 second resolution, because we'd have events which would happen inside the space of a minute, and we couldn't really tell what was going on during that. So rather than polling on 1 minute, now we run it on a 1 second polling interval. So we get really fine stats around where we have issues that we can go back and look at how everything's performing. Another thing that's been invaluable here has been the hardware performance counters that are in the CPU. So on FreeBSD, there's PMC stat, which allows you to look at, for instance, this is looking at the clock unhalted count, cycle count in the CPU. So it's basically where is the CPU at for percentage of time. So you can see in this example, well, you probably can't read it, but the top thing up there says 16%, and it's in process main, which is the big emulator loop, which is interesting, right? Because that tells us that in our particular application, only 16% of the time is actually executing the emulated code. So even if we were able to take, a super hype which eliminated all of the execution time of all the Erlang code, it would only take 16% out of our total runtime. So we've been focusing on other areas, obviously, to improve the efficiency of what our system's doing. But this allowed us a view of things that were happening both in terms of inside Beam. Earlier on, we saw a lot more time in like the garbage collection routines. They're still on there, but they're further down. We saw some issues with the networking stack, which we needed to tune away, and things of that nature. We've done a little bit of dtrace, although that's mostly for debugging, not really for performance. A little bit of kernel lock counting, but we haven't really found any issues that we needed to deal with in FreeBSD that we didn't find out through PMC stat. And then, of course, looking at our code itself, we used fprof. Now, the FreeBSD build of Beam doesn't support CPU timestamp, so I actually patched it so that we could get that as well. And then it may be user error on my part, but I couldn't figure out how to get an aggregated look at the call, or the, I forget what they're called, the analyzed output aggregated across all the procs. So I wrote a few scripts to basically boil it all down, aggregate it all down, give us, here are the routines where we're spending all our time. And the biggest thing probably was the lock counting, compiling the emulator with lock counting turned on, because it turns out that most of our issues were with contention in the emulator, which shows pretty strongly in the output of the lock counting. And we'll talk a little bit about that more in the future slide. So the way that we actually measured what was going on here, a couple different ways. So originally we were looking at trying to do synthetic workload against our systems, which is good for the subsystems we have, which are have really simple interfaces, because it's pretty easy to just drive them hard, like say like a user table, being able to do inserts and reads against that table as quickly as possible from a small number of hosts and generate a tremendous amount of load. But that has really limited value for our user-facing systems, because first of all, if we're talking about supporting 1 million users on a server, we're going to need at least 30 hosts or 30 hosts, or at least 30 IPs, just to generate enough IP ports to be able to open that many connections, and that's just to test one server. And that's just for 1 million connections. If we go higher than that, then we're talking 60 hosts, and it just becomes really troublesome to come up with the right kind of scale. Further, actually generating the type of traffic that we're actually going to see in production is very difficult, obviously. We can guess at what the normal workload is like, and create some behaviors with lots of processes that are going to emulate what our users are going to do. But in actuality, what happens is we see networking events, we see world events, we see all these different things. We have since we're multi-platform, we have very different behavior between our clients, between countries where the people are located. And so the synthetic workload just is very limited value for at least tuning our user-facing systems. Another type of workload testing we did was basically with a teed workload. So we take the normal production traffic and pipe it off to a separate system. And this was very useful for the places that we could contain the side effects. So obviously we couldn't tee traffic and do things that were actually going to affect the permanent state of a user, or was going to result in multiple messages going to users, things of that nature. But in the cases where we could contain those side effects, then this turned out to be extremely useful for being able to tune things, especially with Erlang and being able to hot load code, because we could be running under full production load, have an idea, compile it, load it in as it's running, and instantly see, well, is that better or is that worse? And some of the things I did also were to add some knobs where there weren't knobs before, so that on the fly, under production load, we could twiddle the knobs and see how it would affect. We'd basically be tailing the SAR output and looking at things like CPU usage or VM utilization or dropped listen queue overflows, things like that, and turn knobs and see how the system reacted. But of course, the ultimate test here is to actually give it true production load, so that it's doing not only the input work, which is what it would get if it was doing the teed case, but also doing all the output work as well. And we did this via a couple different ways. One is just to put the server into DNS a couple times, so that would give it double or triple the normal traffic. But that creates issues with TTLs, because because there are a lot of DNS resolvers and clients out there that don't respect the TTL very well, and there's a delay. So if we're trying to push systems to their limit, we get to their limit, it's hard to quickly react to the fact that we're actually getting more traffic than we can deal with. So we tried another approach, which was use IPFW and FreeBSD and basically forward the traffic from one of the production servers to another production server. So the traffic would be coming into two servers, but one of them would forward to the other one, and so we could exactly give it the number of additional client connections that we wanted to run. And that works great, except that we actually panicked our kernels a couple times. There's a bug in there somewhere that occurred a couple times, so we're shying away from that a little bit at this point. Okay, so let's start talking about results. So as we started to ramp up from that 200K number in terms of connections, the first bottleneck started to show at about 425K. And basically what we'd see is that the system would just start, it would stop, and it was just obviously running into a lot of contention. And you could see it. I don't have the I don't think I do. I don't have the data here out of SAR that was showing that, but basically, I'm jumping ahead a little bit in terms of one of the fixes that I was going to talk about. But one of the things I did was instrument the scheduler, and I think it's similar to what's gone into R15 with that scheduler wall clock. But but basically measuring the time that a scheduler is actually executing process code or executing system code, and then the sum of those is how much time it's actually doing useful work versus sleeping or spinning. And in the case where we start to see contention, that number starts to go way up relative to how much CPU is being used, because when it starts to run into contention, it's hitting locks. At least in R14, most of those locks are sleeping locks, and so the schedulers go to sleep, so they're not using any CPU, but yet they're still counting against the scheduler's utilization. So we'd see 35, 40% CPU across the system, but the schedulers are at 95% utilization. So obviously they can't be driven any harder. They're running into each other too much. So the first round of fixes got us to over 1 million connections. And here's what, yeah, the resolution is just horrible here. But you can see here we're at the end here. Open files on that top one is, so there's a few hundred files that are open across the system just for normal operations, but the rest are sockets that are open to our clients. So you can see we're over 1 million there. Our virtual memory usage is at 76%. And CPU is running at 73% or so. And then what Beam looks like here, you can see that the emulator is running at 45%. Where is it? It's in the middle here on the bottom one. 45% utilization in the emulator itself, which matches pretty closely to the user percentage. So that's good. That means, because all the time in the emulator is user time, and so if it matches up well with what the system thinks is being used in user time, then that's, and I forgot to mention one thing. There's a caveat, which is that the schedulers actually, by default, do a lot of spinning, the SMP schedulers, when they don't have work to do. I think the reason for that is so that when they do get work, they're immediately ready to pick it up and start executing it. They don't have to wait for the CPU for the OS to schedule them. On FreeBSD, that doesn't turn out to make much of a difference, especially the way we run it. So we've got a scheduler per CPU. The system's not doing anything else. So it's either going to be in the scheduler's idle thread, or it's going to be executing Beam. So it makes there's really imperceptible difference between spinning and sleeping. And it makes more sense for us to be able to actually put them into sleep, because it makes our CPU stats look better. It allows the system to power down those CPUs so they're not chewing up a bunch of electricity for no reason. Ordinarily, CPU utilization isn't necessarily a good measure of how busy the system is. I think the OTP teams said that a couple times here. But we tweaked it so they don't spin, basically, so those things should match up. So we continued to attack similar bottlenecks, and about a month later, we actually got to 2 million, which was amazing, because like I said, originally 1 million seemed like a long shot, and we pretty easily got to 2 million. Just quickly, you can see what it looks like here. So we've got open files here over on the right-hand side, which is 2 million. Our VM utilization is now up to about 80%, so we're getting close to where FreeBSD is going to start thinking about, I need to reclaim pages, maybe start hitting us with some paging. CPU is about the same as it was with 1 million connections, so we've improved things in terms of overall. So we've doubled our connections. CPU is still running hot, but it's still within the realm of what we can do. Now, if you look at what the scheduler is doing, the scheduler is running at the same as the system's running now. So we're starting to get some more contention, but otherwise the system's still running pretty well. So we got to 2 million, and that seemed like a pretty good place to stop for the holidays. So we put that stuff on the back burner, and then after the New Year, started looking at it. It wasn't clear that there was any more low-hanging fruit to get us past 2 million. So we started looking at the application code itself, the Erlang stuff, and started doing some profiling there, and found some things that we did. One of the things we did was, and I think it shows here, yeah. So originally we had 2 processes per connection. We cut that in half, so there's only a single process per connection. That helped a lot. We did some things with timers, and I'll go into more specifics in a little bit. But we had kind of we were playing around with the DNS, doing the double DNS, and we ran into the issue with the long TTL, and we actually had an unintentional, we were trying to get to about 2.3, 2.4, and this particular box actually ended up keeping going, and eventually peaked at about 2.8 before we kind of intervened and said, okay, that's enough. We need to figure out what's going on. At that point, it was doing 571,000 packets in plus out per second. Within that, 200K of those were distribution messages. So it's just, and let's see, some of these other stats. CPUs running at 86%. Our VM load is down to 70% now, so we made some memory optimizations, and otherwise it's keeping up, which was really remarkable. So then it seemed like, well, heck, if we can do 2.8, we must be able to do 3, right? But haven't gotten there yet. Tried to get there on St. Patrick's Day, but it didn't work. We kind of aborted that test because, well, it was Saturday, and the systems started to show a little bit of backlog. So one of the things, basically what we see in our systems when they fall behind, as I'm sure a lot of people see, is you start to get message queues that start getting long. So one of our biggest measures of the system getting into trouble is either a single message queue getting long or a sum of message queues getting long. And then in this particular case, let's see. Well, I don't have it in the SAR output, but the thing below it is another. Uh-oh, how did it go back so far? Pardon me. Is another tool we use. So one of the things that I added to Beam was instrumenting the message queue activity per process. So how many messages are being sent, how many messages are being received, how fast they're being sent, how fast they're being received, and that allows us to do things like this, which is look at a process by process basis. So here's sort of every 10 seconds. So our logging notices that there's message backlog. It starts logging every 10 seconds, showing us which process, what the backlog is. So this particular process has 600,000 messages in the message queue. Its DQ rate out of that queue is only 40K. So that means it's got a queue delay of 15 seconds, which is we'd like 0 or almost 0. But it is draining. I mean, it is draining. It's not filling faster than it's draining. So the estimated time to drain is 41 seconds. So 10 seconds later, the DQ rate's gone up to 46K. The message queue's down to 360K, and the time to drain is 17 seconds. 10 seconds later, it's almost drained. It's down to 160K. It's draining at 48K. Or actually, it's draining at 22K. The DQ rate is 48, but there's an NQ rate, so the difference between those two is 22, so it's draining 22K messages per second. We're down to 7 seconds to drain. So anyway, so this was a little blip while we were running this test that it recovered from, so we probably could have pushed it a little harder, but it wasn't clear that we were going to get to 3 million, so we abandoned it. And in this case, this test got us to about 2.7. All right, so on to some general findings. How am I doing on time? Good. Obviously, Erlang has awesome SMP scalability. I'm just blown away. So this is a 24-way box, and we can run this system at 85% CPU utilization, and it's keeping up. I mean, it's doing production load. It's not blowing up. We can run it like this all day. So the combination of our code, Beam, and FreeBSD is looking really, really good for SMP. And here's a little graph of that experiment that week. So what this is number of connections on the x-axis, CPU utilization on the y-axis. And you can see there's a couple different kind of parallel lines there. So what that is our daily traffic goes up and down. And after we restart a server, it starts to accumulate some long connected clients. Some of our clients are short connected, some of them are longer connected. So the longer a server's been up, the higher percentage of long connected clients it has, which are kind of idle. So it can actually handle more connections because it's not as busy on each connection. So those parallel lines are basically day by day as it's accumulating more of these long connected connections. It has to do less work, so that's why they're shifting out to the right. But overall, you can see that kind of looks linear, right? Upper corner is 100% CPU, lower corners, so we start out with no connections at a little under 10%, and when we get up to like 2.5 million, we're up above 90%. But it's pretty linear in there. So if you look at a lot of software that's not as good at scaling across multi-core, that curve's going to look like that. It's going to start going straight up at some point when you start to get a lot of contention across the processor. So this is just remarkable, I think, and it's a real testament to the programming model in Erlang, and just a fabulous emulator, and then a few fixes that we found along the way. So the biggest thing, obviously, was contention. That's what got us from 200K to 2 million. Those were all contention fixes. Some of them were internal to Beam, some of which were addressable with app changes. So there were things we discovered about the way Beam would deal with a certain Erlang usage, and so we could change that in our code without having to patch Beam. But some of them required actually having to patch Beam. And then other ones required some app changes, partitioning workload so that it's not crossing processors a lot or hosts, and then avoiding some common things that come at a price. And I have more specifics. So here's some of the specifics. So FreeBSD, quickly we backported a TSC-based time counter out of FreeBSD 9 into FreeBSD 8. The TSC is on board the processor, and it ticks once for each cycle, and it's very cheap to read. So it's very easy to do. It's very fast to get time of day calls, much less expensive than going to one of the I/O chips to get the time of day. So that helps a lot. We backported the IGB driver from FreeBSD 9 because we were having issues with the multiple queues, interrupt queues on the on the cards locking up. And then just some obvious sysctl tuning for increasing the number of files and sockets. But the one thing that we noticed out of PMC stat was spending a lot of time looking at PCBs in the networking stack. So bumping up the size of the hash table for the TCP PCBs was a win as far as reducing that time in the kernel. Okay, so on to some of the Beam patches. So I mentioned that I instrumented the scheduler to get utilization in terms of process execution time, system execution time, number of context switches, number of waits, number of sleeps. Added the statistics for message queues. So that's across all the processes. So it's you can do that in Erlang code by doing process info and then adding them all up, but it's tremendously slow. And when we've got millions of connections, it grinds the system to a halt if you try to do that. So there's actually loops in Beam which are highly optimized for getting the list of processes. So I added one to actually get us the message stats, the message queue stats out quickly like that, so that we can actually do it in production when we have 3 million or 2.5 million connections going without busting the system. Process info, I mentioned the message queue stats, NQ, DQ, send rates, counts and rates, and it has 3 different decay intervals, so it'll show you the 1 second interval, and these are approximate because it just does some very simple math to decay these, but 1 second, 10 second, 100 second intervals. So that allows us to kind of, if we're having an issue, we can go in and see like, okay, this process should be running at this speed, or it's running this speed this minute, and it's running this speed this minute. There's something going on there. And then statistic message counts, which is just an aggregation of all the message queue stats in terms of the rates. And then I fixed the lack of CPU timestamp in fprof for FreeBSD. I had to make lock counting work for larger async thread counts because it blew up once you went above 64 async threads without that. And then added a couple options to the ERTS debug lock counters because if you try to do lock counting with a whole bunch of, let's see, one of them, so there, you can turn off process locks counting, but you can't turn off port locks. And since each of our processes has a port, the TCP port, it didn't do us any good. So we needed to be able to turn off port locks too, because otherwise you'd get millions of these lock counting statistics running. And and we know those aren't going to be hot because those are just individual connections. So there's no contention on those. The locks that we care about are the sort of the system locks. So we need to be able to turn those off. And then just fix some missing counting for outbound disk bytes. There's a couple missing increments there. As far as tuning, one of the first things we did was set the scheduler wake-up threshold to low because on FreeBSD we were having an issue where schedulers would go to sleep and they'd never wake up. And then another one would go to sleep, and eventually you'd have two schedulers running at 100% and the system falling behind. But SWT low solved that. We bumped up the MSEG maximums so that the memory allocators would prefer MSEG over malloc. And that's important for another reason I'll tell you in a sec. We wanted an allocator per instance per scheduler, which I think is the default in R15 now. And then we configured the carrier sizes so that they start out big and get bigger. So they start at 2 meg and they go to 32 meg. And the reason we want that is we want 2 meg aligned, big chunks of 2 meg aligned malloc memory so that FreeBSD will do automatic promotion to super pages. So that reduces our TLB thrash rate and improves our throughput for the same CPU. We run our schedulers, we run Beam at real-time priority so that other things that we do on the box, cron jobs and things like that, don't interrupt the scheduler because we did have issues with that. We'd be running along smoothly and all of a sudden, for a few seconds we'd glitch the system. We get a huge backlog that it could work through, but we want the schedulers to get top priority on execution resources. So we run them at real-time priority, and then all the cron jobs and everything just get scheduled as possible. And then I mentioned dialing down the spin counts so that the schedulers wouldn't spin. That was a patch. As far as beam contention, I mentioned contention was a big thing. One of the big ones is the time of day lock, and especially time of day delivery. So I believe, as I recall, every time a message is delivered from a port, it looks to update the time of day, which means, and that's a single lock across all schedulers, which means that all the CPUs are hitting one lock. That's bad. So there was a little bit of optimization there. On the timer wheel itself, I did a little bit of optimization there. There's two levels of timer tracking. There's the timer wheel, and then there's the BIF timers where if you're actually creating, so the timer wheel is used for timers, BIF timers, and for like receive timeouts, things like that. And then there's a separate table for just the BIF timers. And that's it's not a very wide hash table, so we had multiple timers per connection, which meant that hash table was just not wide enough. So we made it wider. It was still a source of contention, so we ended up getting rid of those BIF timers and moving everything to just receive timeouts because that just uses the timer wheel and remove the BIF timer lock out of the equation altogether. There's a thing called the check IO table, which grows arithmetically, which is bad for us. Created lots of VM thrashing problems because it would allocate a table this big, then this big, then this big, then this big, then this big. Improve that to just do a sort of a geometric allocation of that table. Get rid of that. We added a prim file, write file that takes a port, so that you can write a file atomically with a port that you already have open instead of having to open the port every time, and that reduced contention on port creation, which was a big issue. And then there's just a minor thing. There's an MSEG. Every time it allocates an MSEG, it has to check to see if it's over the maximum number of MSEGs allocated, and that's a single point of contention across all the processors, across all the allocators. Now, I think in RF15, MSEG allocators are per scheduler, so that's not much of an issue there. And then there were some issues with lots of port transactions when accepting a connection. So there were a couple changes to setting the options on that so that there weren't as many port interactions, which are expensive in terms of contention. In terms of OTP throughput, so we were running into issues where when the message queue, in these situations where we were dealing with a backlog, since GC runs through the message queue, the longer the message queue is, the longer the GC takes, and so we could get into these destabilizing, these unstable situations where it could not recover. So we added in some code so that it would back off on the GC if the message queue got long, and then once the message queue resolved itself, then go back to normal GC parameters. We had an issue with the dist receive buffers. When it's receiving over the dist channels, it's reading 4K at a time, which for some of our high throughput systems is just not big enough. There's too many reads going on, so making that configurable and setting the default to a reasonable number was good for us. One of the big issues that we had with Amnesia was we're using async dirty, so no transactions, just as simple as you can get. But we'd run into a backlog when we're doing remote replication. It still goes through Amnesia TM on the remote, and that's a single process. So we parallelized that by basically launching a separate process for each table that's getting the async dirty updates, and that allows it to parallelize the updates to the underlying ETS tables, and that created much more throughput for us. What's that? Okay. I think, let's see, where am I? Let's see. I'll just quickly name these, and then you can ask me questions. Issue with PG2, we increased the size of the MSEG cache. We moved all our code from using Erlang now, which is takes a single lock, to using OS timestamp, which is very fast. We got rid of our normal gen server calls because when we're going remotely, because that causes an extra message to go for the link. And then partitioning, let's see. Yeah, if you're super interested, you can ask me after or look at the slides after, but questions, quickly. I probably have time for one or two. Yeah?
That was just a lot of stuff. Are the slides going to be available?
Yes, they are. Absolutely.
All the patches you made, are they going into our OTP release system, or are they available somewhere?
They're up on GitHub, and right now we don't have a WhatsApp account yet. They're in my account, which is readr, but they're all there, both against R14 and R15. Now a lot of these have had no testing outside of FreeBSD, so I don't know how soon we could possibly get them into OTP, but they're at least they're available there for people to look at. I'm sorry? Yes. Yeah. Anything else?
All right.
Thanks very much.